And initially, I just showed you how to calculate probabilities on the z-table, just kind of pulling straight off. If you don't have a z-table, so you'll want one today because we're going to use these again. So make sure you have a z-table. If you don't have one, I got a stack up here, but you will want one to work along today if you forgot to bring one back. So I showed you how to work directly with a z-table, but also I showed you how to solve problems about normal distributions, even if they weren't, standard normal. It just involves calculating z-scores and then getting probabilities off the z-table, right? And so that's where we left off. What I want to do today is I want to talk another way that we can use the z-table, and then we may actually get into a little bit of conversation about the next topic, which is sampling. But it all kind of relates back to the z-table. So what we didn't get to was we didn't talk about percentiles last week. And so what is a percentile? We sort of mentioned this way back. What does a percentile measure? It is. I mean, you could think of it as an area or probability. But like just in practice, what is a percentile? Yeah, it's a measure of relative standing like the z-score, right? And it's the percent of the population, right, that's at or below a cutoff, right? And so, like, for example, if you're in the 80th percentile, what does that mean?
80% of people are...
Yeah, 80% are either at or below you. Right? So if you're in the 80th percentile for height, you're as tall or taller than 80% of people. If you're at the 80th percentile on an exam, that means you outscored 80% of people. Okay? So percentile just measures the percentage at or below. We can actually calculate percentiles on a normal distribution. So like you can picture that. So on the normal distribution, if you were in the 80th percentile, where would you be? You'd be somewhere above average, right? And you'd be somewhere on the normal distribution such that the area below you, right, on the distribution is 80% or 0.8. Okay? So when you look at it that way, like on that picture, the picture shows us that we should be able to calculate percentiles on a normal distribution using the z-table. What we're going to have to do, though, is we're basically going to have to read the table in reverse. Because before, I had given you the cutoff, like I showed you a value that I wanted you to look up, and then you went and looked up in that value and you found the area below it. But now I want to read it in reverse. I want to be able to give you an area, and you come back and give me a z-score, essentially. All right? So I'll show you how that works. So, like, for example, let's suppose we wanted to find the 95th percentile for a z distribution, right? So what I mean when I say that is I want you to find on the normal distribution how far up do you need to go, or in other words, what z-score would you have to get in order to have 95% of the normal distribution below that z-score. That's what I'd like to know. All right. Now, is that z-score going to have to be positive or negative? It's got to be positive because it's above average. So you can know that you're going to be on your positive side of your z-table. And then if you go to the positive side of the z-table, I brought mine up here. Okay, there's my positive side. How do I find the 90th percentile? Exactly. So we're going inside the table, and what we're looking for is we're looking for 0.95 in the table, right? I'm searching through my table. And if you look in there, where do you hit it? About?
1.64.
Yep. Go down this row, 1.6. Yeah? And you scroll across, and you'll notice right here, you're just under the 95th percentile, right? Because it's at 0.9495. And then right here, you jump up over the 95th percentile. Now, is either one of those closer than the other in this case? In this case, they're not. They're equidistant. This is a kind of a special case. This usually doesn't happen. But sometimes it does, so that's why I use this as an example. Sometimes what you'll find is that the two probabilities or the two areas are equidistant from the area you're trying to find. And if that's the case, what we could do is we could say, okay, well, what's the z-score associated with 0.94 and 95? right? It's 1.6. So the jump happens somewhere between z equals 1.64 and z equals 1.65, right? So if they're equidistant, what we tend to do is we just tend to average those z-scores. That's what you do if they're equidistant. So if I was going to find the 95th percentile, and right, what I'm doing is we're tracking it back, we're reading the table backwards, right? That's how I'm getting 1.64 and 1.65. I'm finding the area first, and then I'm mapping it back out to its first and second decimal place. Okay. So in this case, though, these happen to be equidistant. Okay. And so to get that calculation here, we would actually do the average. So let me go red. I don't want to pull it all the way back up because I have to. So we go 1.64 plus 1.65, average them out. And so we would say that the z-score you need to be in the 95th percentile would be 1.645. That one would average. And so you average equidistance. Okay, but you average the z-scores, not the probabilities. If you average the probabilities, they just come out to 95% because they're equidistant. So you average the z-scores. All right. Now, if you want to find the 80th percentile, that's the one I drew on the last slide. So first off, I guess before I go on, does anybody have any questions about where I got those two numbers or why on the z-table? Back on the table, 1.64 or 1.65? Why we picked those? Okay. Now, if we want to go find the 80th percentile on the z-table, all right, so we're scrolling back through our table, Where do you hit it?
0.84.
Yeah, so here, let me get rid of my, I think these are distracting. Where's my eraser? Come on. Okay, so when I'm scrolling through my table, Here's 0.7995, that's below the 80th percentile. Here's 0.8023, that's above the 80th percentile. Which one's closer, though? We go for the closer probability. So you don't always pick the one below, you don't always pick the one above, you just pick the one that gets closest to the percentile you're looking for. And then this one, like you said, what's the z-score associated with? 0.84. Yeah. Okay. So then, wrong one. So our z-score would be 0.84.
But it is possible to have a more precise z-table, right?
It's possible to have a more precise z-table. It's actually possible to have an infinitely precise z-table because there's actually a function that describes this that curve. It's a really complicated function. You don't need to write this down, but you could actually. There is a function. It's an exponential function. It's like 1 over sigma e to the x minus mu squared over sigma or something like that. It's like some function. I might have gotten the details wrong with that. But there is actually a function that describes that. And then you can use calculus to integrate and actually find very precise areas. So what the computer's doing when it calls back a z-score for like a certain percentile, it'll actually tell you the answer is 0.84 something, 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 something. And it's returning it from the function itself, not from the table. The table is just an approximation of the function that we use, so we don't have to do complicated math and stuff. It's kind of so that's the answer. So yeah, and actually in a software program, they don't call tables, they just call the functions. But the tables were made using the function, if that makes sense. Yeah. Okay. All right. Okay. So we just do, for the sake of this class, we go as precise as the table goes, and that's it. So on your quiz, make sure that you're using the table to get your z-scores and stuff. Don't call a function on like Google or something. It'll work. You'll get the right answer. It just won't work for our quiz because my quiz is based on this table. Okay. All right. So how do we use that and track it back to percentiles of normal distributions with other means of standard deviations? Well, essentially, we just map the process backwards that we did last week. So in this case, if I wanted to find the 90th percentile of cholesterol levels, so before we started on our distribution, we calculated a z-score, then we went to the z-table. Now we're going to do the process in reverse. Okay? So we're going to start on the z-table, and first we're going to find the percentile we're looking for. Okay? So first I'm going to go to my z-table, and I'm going to find the 90th percentile. So you're going to go to the positive side. You're looking inside the table for the number that gets you closest to 0.90. Where do you hit that at?
Can I hit that at?
1.2.
Yeah, if you look at 1.28 and 1.29 on your table. Okay, I can pull it up here. Right? At 1.28, you're at 0.8997. Then you jump up to 0.9015. Which one of those is closer to 90th percentile?
18997.
That's a little bit closer, right? Because it's 3 10,000ths below. The other one's 15 10,000ths above. And that's associated with a z-score of 1.28. So that's the z-score that we need. All right, so we'll go 1.28. All right, but that's not actually what I'm interested in. What I'm interested in is I'm interested in the cholesterol level. You know, what's the cutoff in cholesterol levels that you'd have to hit to be in the 90th percentile, right? How do you get that? Yeah, we just use the z-score formula. We're going to be using it a little bit differently, right? So the z-score formula, you know, when I was giving you problems the other day, I was giving you the observation, the mean, and the standard deviation. We were calculating z-scores. Now we know the z-score, we know the mean and standard deviation. We just don't know the x, the observation, the cutoff. And so, but we can find it, right? Because we know what z-score we want. We know the mean, and we know the standard deviation, right? So this is just an algebra problem. How do you solve for x? Well, first, you'd multiply the 36.2 over, right? So then you'd just be left with x minus 180. And then how do you solve for x? You would just add it, right? So you're just going to do 1.28 times 36.2, and then you add 180, and then what does that come out to be? You got like 212 or something, didn't you? You got 226.
Yeah. Well, I did it from I did the 180 plus the 0.8997 times 36.2.
No. Oh, no. You want to multiply by the z-score.
The z-score.
Yeah,
okay.
so we're taking the z-score, right? Because the z-score formula uses the z-score,
Right,
not the
it's not the
percentage. Yeah.
Oh, okay. That's what it's done.
So if you calculate this out, it should come out to, what did you get? 226 point something. Other people get something like that? Yeah? Yeah? So it's 226 point, say, what did you say it was? 336. So like 226.3 or something. Okay. Okay. And that would be the solution there. Okay. So it's like you work it backwards. You start from the probability, the percentile. That gives you a z-score. The z-score can then be turned back into an actual value, like a cholesterol level. Okay.
3.62, that's why.
Yeah, let me see here. Let me go one more. I got a new slide. Okay, before I go to the next question about that, I'll show you one other quick example. Question about that one, though? You can shortcut it a little bit, because if you notice where the z-score, the way the z-score formula is, right, the steps are always going to be the same, right? You're always going to be multiplying the sigma over and then adding the mu. So one way people will, if you remember it that way too, to solve it the other way, the observation is always going to be the mean plus whatever z-score it is times sigma. So you can map it that way. So, okay. So we can do one more example. Let's say, for example, I thought I had another one in here, but I'll do one real quick. Let's say heights of males have a normal distribution, because they do. And let's say the mean is 70 inches. I don't know if that's true or not, but let's just say it is. And let's say the standard deviation is 2.7 inches. Okay, and let's say I want to find the I don't know, why not the 15th percentile or something?
2.7 inches?
Yeah, we'll say 2.7. So let's find this 15th percentile for male heights. So how short would you have to be in the shortest 15% of men, if that's the distribution of male heights? Okay. So first we need to do what? We got to go get our z-score. And now is this one going to be positive or negative? This one's negative because it's below average, right? So we're going inside the table and we're looking for the 15th percentile. How close can you get? You see right there, go to -1 row, the -1.0 row.
5.7?
Yeah, that's the one I got, which is 0.
Wait, so
Or would it, yeah, 0.1587.
No,
One.
point 15.
go further. Yeah, go further down that row. Go further down that row. Here, I'll just pull it up.
Point 1492.
Yeah. Yeah, so we're going for the 15th percentile on the negative side. Go to the -1.0 row, right?
Yeah.
Here's where the jump gets made. The negative side reads in reverse because you're gaining probability going the other way.
Yeah, that's what I
As you go
thought.
through. Yeah, so right. So here you make the jump from just under the 15th percentile to just over the 15th percentile. Which one of those is closer? This is a little bit closer, right, to 0.15. And it's a z-score of negative 0.001234, so negative 1.04. That'd be your z-score. Okay. So negative 1.04. So that's the z-score we need. Now this is where it's nice just to have the shortcut kind of formula plugged in. Now I can map that back to a observation very quickly, because what I'm looking for, right, is I'm looking for a height, because heights are centered at 70. I'm looking for how tall in inches that person would have to be, right, an x value. But I know that I can just take the mean plus the z-score times the standard deviation. In this case, it happens to be a negative z-score, so it's going to be subtraction from the mean, right? And so that'll be, what is negative 1.04 times, well, what does it come out to be? You can just tell me the answer. 67.2
Yeah, 67.
inches. So that would be your. Okay. All right. Does that seem okay? Everybody feel okay about that? Okay. So you can start on normal distributions and calculate z-scores and go to the z-table, but you can also map it the other way. You can start on the z-table and you can get percentiles, and then you can take those z-scores and map it back into actual values. Go both ways. Yeah? Okay. Now, there's this other notation which is kind of goofy, but we're going to need it in Module 8, so I'm just going to introduce it and I'll show you how to find it. But there's this notation called z-alpha. So that's a little Greek letter. It's a lowercase alpha. And what z-alpha notation is I'm going to draw it first. It's the z-score. It's the z-score such that the area above it is alpha. Okay. You can it's almost like,
Sounds like greater than.
yeah. So it's the score such that the area above is equal to alpha. It's like the opposite of a percentile, basically. So percentile is where that percentage is below. But in the z-alpha notation, it's the z-score such that the area above is that. And what it looks like. It's never actually going to be an alpha right there. There'll be a number in its place. So it's like it's a subscript. And so, like this, for example, this is going to be the z-score such that the area above it is 0.025. Okay. Notice that the so it's pretty much all, I mean, in practice, the way we're going to use it, it's pretty much always positive. So it's always going to be a positive z-score, because normally this number that's in the subscript is going to be small, like 2% or 5% or 10%. It's not going to get. It's never going to be like z sub 0.95 or something. We rarely use negative z alphas. But anyways, so this one. So if I were going to try to find, I'll show you this example. Z sub 0.025. What I'm looking for is I'm looking for the z-score such that 2.5% is above. Now, there's a couple ways to find that. Can anybody think of one way we could find it? Yeah, one way is we could just figure, okay, if 2.5% have to be above, how much has to be below? Yeah, so you just do 1 minus 0.025, and that's 0.975, right? And so essentially what are we looking for? We're looking for the 97.5 percentile. That's what we're looking for. Okay. If you go inside your table, now this is going to be a positive z-score. Where do you hit the 97.5 percentile?
That's between 2001.
I think you hit it exactly. Go to the 1.9 row.
Oh, you're right.
Yeah, look at the 1.9 row. Do you see it? 1.9. Go to 1.96. Yeah. You actually hit it directly if you look in the z-score table. Right. 1.96, right there. You hit the 97.5 percentile exactly at a z-score of 1.96. Yeah. So that would be, and the applications of that, it's like, it doesn't really matter that much. I'm going to show you what they are later. But right now, you just need to understand how to find it. So that's what that notation means. It's the z-score so that that amount of area is above it. Is there another way we could have found it?
Oh, if you do the reverse of it.
Yeah, you could. Remember it's symmetric? So we could have just looked up this number on the negative side. If you go to the negative side of your table and look up 0.025.
Negative 281.
Yeah. Yeah, see right here? 0.025. What's the z-score? Negative 1.96. So you could just look it up on the negative side and just remember that the z alpha is the positive version of it. So there's two ways to find it. One way is to know, okay, if that's how much has to be above, we can just figure out how much it has to be below, do 1 minus, and then look that up on the table. Or we can remember it's symmetrical, and we can look it up on the bottom side, and then just use the positive version of the z-score. Does that make sense? Yeah. Because, if it's the same on both sides. All right. Okay. One more. If you were trying to find z.05, so like you're trying to find the z-score such that 5% is above. Okay, well, what does that mean? If 5% is above, how much is below? Has to be the 95th percentile. If you go try to find the 95th percentile, what happens? We actually already found that one. You guys remember?
It's in between.
It's in between 1.64 and 1.65. So that's one of those that we average. Yeah, we already found that because z sub 0.05 is actually exactly the same as the 95th percentile. So it's essentially, it's the same as finding a percentile. It's just a different notation. And we'll figure out later on why it's important or why we would use that notation. But We do. So there's also, you'll notice there's some numbers down at the bottom of your table in here, and some of those are numbers we already looked up, and they become important in Module 8 and Module 9. So not yet, though. You don't have to worry about them yet. So it's on the positive side I'm talking about. It has these like summary tables on the positive side. But anyways. All right. Any questions, though, about this problem or anything that I showed you today about finding percentiles off the z-table? Okay. That gives you pretty much everything you need for the quiz. That's the one I had moved, but it's due. So that one's due today, if you haven't already taken it. Okay. I do want to get into just a little bit of the next modules just to show you, because I don't have I want to show you some actual data and some graphs and stuff. So that's a good thing to do today, and then tomorrow we'll do more of the calculations with the table. So I do want to jump into Module 7 just a little bit. I want to make sure that we get as much out of the way here before next week, because if you don't remember, and I was mentioning at the beginning, next week, starting in the middle of next week, I'm going to be gone for a while. I'm going to post lectures online and give you guys activities and stuff to work on as we're going, and then when you come back, we'll do some review as well. Obviously, I'm not going to leave you out to dry. And it's just one module that it'll end up covering while I'm gone. So we'll get through Module 7 and 8 this week and next. Module 9, I'll deliver a good chunk of that online, and then we'll do some review when we come back. And that's all we really have left. We only have like 3 more modules left in the class. So with that, though, I do want to get started on it a little bit. Any questions about that? So it doesn't really change anything for my online students, but okay. So we did this. We talked about number of siblings in one of our previous examples, like when we were talking about discrete distributions. Now the thing is that typically speaking, we know that in the big picture, right? Like there's typically some big population, but you're not actually going to be able to talk to anybody or talk to everybody. You're going to have to take some sample from that group. True? Okay. So like so the way I usually introduce this is I think of this people in this classroom as a population. Like everyone in here is everyone who exists as far as we care or something, right? Okay. So what I want to do today is I want everybody to tell me how many siblings they have. And I'm actually going to record it in this thing called StatCrunch. did I show you guys? I did this before. Did I pull this up for you guys before? Okay. I don't think so. But StatCrunch, it looks a little bit about like Excel. It's just this program. It does some data analysis and stuff. I don't make you guys buy it because it costs like $40 or $50 or something for the quarter, and we wouldn't use it enough to justify it. But I'm just going to show you some stuff that it can do. I'm going to record the data in here, and then we're going to use it. I want to see what happens when we start sampling from a population. So we'll just go around, and then you guys just tell me how many siblings you have. And that would be brothers and sisters who are not you. And you can count step siblings or not, however you count them, all right? So Paul, we'll just start with you, and maybe we'll go down the rows and down the rows and all the way back, and we'll get everybody's number of siblings. So one sibling. All right, so we'll cross. 2. 1. 3. Then we'll go back to the second row. 3 siblings. 2 siblings. 5 siblings. 3. 5. 3. 3. 3. 4. 1. None. 3. How many? 1. 1. 5. Okay, I have 1, so I'm going to count myself in there. All right. So it looks like the most common is 4 families of 4 kids. That's the most common, right? 3 kids? Or 3 siblings? Anyways, all right. So anyway, here you go. Okay, now we could, here, let's add one more. Gina, how many siblings do you have?
I have
2
2.
siblings.
I have one.
1. You are one of 2.
Yeah.
Yes.
It's Monday.
It's more common than you think for people to give me the number of actual kids in their family versus how many siblings they have. Okay. So we could actually, the nice thing about little statistical packages like this is kind of like your computer or your calculator. They can do some summary statistics really fast. So for the number of siblings, I could get like the mean and the standard deviation really quickly. I could also pull out the median. stuff like that. Technically, actually, if we're going to treat this like a population, this would be we would do the unadjusted standard deviation. But anyways, it's pretty quick, right? So
Is the unadjusted one the only one that we wouldn't get on our calculator?
it's where it doesn't do the -1. Yes, the sigma versus the s. Anyways, but like you can see here, on average, as a population, like if the population was everyone here, we have 2.4 siblings. The median number of siblings is 3, and the standard deviation is about 1.5 siblings. So that's like our population data. Okay. But let's say, for example, that someone else comes into the room and they don't see this information, like they don't have access to this information, and I say, okay, I would like you to estimate the average number of siblings that we have, that the people in this class have. Okay, that's what I'd like you to do. But I'm not going to let you talk to everyone. You are only allowed to talk to like 5 people. That's what I would say, right? Okay. Well, how would they have to do it then? What would they do? Pick 5 people. Hopefully they do what? A random sample. Hopefully they use a random sample to get those 5 people. And then they talk to those 5 people, and then you'd average those out, and that'd be your best guess. Right? That's about as good as you could do if you weren't allowed to talk to everyone. Okay. We can look, by the way, at the histogram of our sibling data. It's kind of a weird distribution. It's a small data sample set. But, this looks like kind of skewed-ish. I don't know. Well, it's pretty symmetrical. Most of us are piled down here. Okay, so what I want to do, though, is I want to say, okay, I can sample with this computer pretty quickly. So in the data option, I can do a sample. So from the siblings, I could actually sample 5 people. And it'll just pull 5 people out randomly. It'll use an SRS. It'll pull them out, and then it'll drop them into a category here. So in the first, if I were the first person to walk in and I took a sample, I would have sampled someone with 1 sibling, 1 sibling, 1 sibling, 3 siblings, 1 sibling. Okay. Now, if I were to do that, what would my guess for the average number of siblings be? Well, if you add them up, right? Add them up and divide by 5. I don't think it'd be 0.1.
It's 1.4.
It's like 1 point, yeah, is it 1.4 you did it? Yeah, it's 1.4, okay? So if this person came in and got this sample, they would guess that there's 1.4 siblings. And are they right? No, they're not right. The real mean is what? 2.4, okay? So they would be wrong, and they would have underestimated the truth. Now, what happens, though, if another person comes in here and does their own sample? What do you think is going to happen? They're going to get a different sample, right? So the next person comes in and they sample, and they talk to someone who has 4 siblings, someone with 3, someone with none, someone with 1, someone with 2. What's their mean? 2.0, even. Are they right? No, they're not right. Their mean is too low. This person's mean was too low. And that happens. What's going to happen if the next person comes in and samples 5 people? They're going to get different data, right? So this person would have got someone with 5 siblings, someone with 3, someone with 5, someone with 1, someone with 1. What's their average going to be if you add those up and divide by 5?
7.5.
What's that?
7.5.
That should be 7.3.
3?
So you come out to 3 even?
Yeah.
Add them up and divide by 5.
Yeah.
Yeah, this person would estimate that we have 3 siblings on average, right? So this person would have said 1.1, this person would have said 2.0, this one would have said 3.0, right? They're all going to get different answers, is the point. And then some of them are going to underestimate the truth, and some of them are going to overestimate the truth. In fact, every single time you redraw from the sample, what's going to happen? It's going to be different. So the nice thing about computers is they can do things very fast. So let's do it a lot, because I want to look at graphs. All right, so let's say I let a bunch of people come in here and sample our class 5 at a time. And let's say, let's do it for like 500. I don't know. Let's say I'd let, so we already did 3. So let's do another 500. So I'm going to let 500 people come in here and sample our population. Okay. And then I'm going to hit compute. And then boom, there you go. So StatCrunch just produced 500 different samples of size 5. Does that make sense? It did it 500 times. Just picked up 5 people, threw them back. Picked up 5 people, threw them back. Okay? Now, what we're actually interested in, though, is the means, right? So what I want to do is I can take, for summary stats for columns, what I can do is I can take all those right there, all those 500 samples, and all I really care about is their means. I'm going to store that in my data table. So what it did is, and this was the numbers we just came up with, right, is that the first person, they would have got a mean of 1.4, the second person got a mean of 2, the second person got a mean of 3. There's like 500 means that I just calculated. You can scroll down and see them all if you really care. It's not that interesting, but they're all there. Okay, so what I want to look at, though, is first, let's get, I got all these columns. We don't need all the actual samples. What I care about the most is the means. Okay, so what I'm going to call this rule, so our first was our original data. I'm going to call this, so X bar, because that's what mean is. I'm going to call this X bar when people were allowed to pick 5 people at a time. So n equals 5. All right. So then what I want to do is I say, okay, I'm going to do a histogram. I want to see the original data and the sample means, and I want to stack them on top of each other. So there you go. So what do you notice? So there's our original data on the top. It's almost what we call bimodal distribution. You have a big spike in one place and a big spike in another. Okay. Now, here is all of the different sample means that the people came in and calculated when they were allowed to sample 5 at a time. What do you notice?
It's pretty symmetrical.
Yeah, it's a lot more, it's symmetrical, right? This is symmetrical. And what else do you notice?
There's spikes where there's an increased number of
Yeah, we're still seeing some of the weirdness from here, like the double spike.
the mode.
Yeah, you know. But what's happening to the shape overall? It's kind of getting that, we're kind of starting to see a little bit of a bell shape, right? You still getting the spikes a little bit, right? Also, what do you notice about, like, what's the smallest mean that was recorded? What's the smallest sample mean? Down here on this one. Nobody got any guesses less than 1. And what's the highest? Nobody really got many guesses much higher than 4. So everybody who would come in and sample with a simple random sample, a lot of them would underestimate the truth, a lot of them would overestimate the truth. But, not by too much. The shape looks almost normal, and then you notice, like, in our original distribution, the answers were anywhere from 0 to 6, but by sampling a few people and averaging them, our range has reduced. Okay? So what do you think would happen if we were allowed to pick 10 people instead of 5?
It'd be more accurate.
Should be more accurate, right? So let's do that. So if I were to sample the sibling data, now I'm allowing people to come in and I'm allowing them to talk to 10 people instead of 5. So they should have better information. Their guesses should be better because they get to talk to more people. And let's say I let 500 people come and do that. So there you go. StatCrunch just delivered me 500 random samples of size 10. But again, what I really care about is the mean. So I'm going to average all those out. So for each of those samples, we'll calculate the mean. I'm going to store them out here at the end. So there you go. And you can see just by the numbers, right? Everything's getting a lot closer to 2.4. But if I go through my data here, I'm going to compare them again. I don't really care about those. Excuse me. My children are on a mission to kill me this year. I've been so sick. It's ridiculous. N equals 10. Okay, so now these are the means when we're allowed to have this. So let's see. Let's go graph, histogram. So there's original data, the one we just saw. Now we'll add this one on top. 3 per page. There you go. Let me spread those out for you. What do you see? Yeah, the shape has become more bell-shaped, right? We no longer have 2 peaks, right? It's starting to look like a nice a lot nicer bell curve, right? What else happened?
They got rid of whatever
The
the size are.
Yeah, the tails have kind of shrunk in, right? So as we take more samples, the variability is going down. The shape is turning into a nice normal distribution. Yeah? And but in every single case, where is the mean? The mean doesn't change, right? So it's like when you're allowed to randomly sample from a population and calculate averages, the more people you sample, obviously, the closer your guesses are going to be to the truth, right? So you don't see as extremely bad guesses in either direction. People are getting closer. But some people are still going to get an overestimate, some people are still going to get an underestimate, but on average, they're going to get it right. You know? If you were allowed to sample 15 people, what do you think would happen?
Get more accurate.
Yeah, we might as well do it because we got a second. I'm going to do it one more time. So I promise I won't do this again. But let's say I let you take 15 people at a time. So their StatCrunch did it. Again, I'm just going to keep the means though. So here, means. And then, so there's all the means. Now you can see they're getting a lot closer to 2.4, right? Let me get rid of all that extra junk. And then rename this. This is x bar in equals 15. And then we'll do one more, right? Boom, 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 boom. That's 4 histograms. And then, it's not perfectly bell-shaped, right? But nothing is going to be perfectly bell-shaped. I mean, you're never going to get a perfect normal distribution. But it's still retaining that bell shape, and it's just getting more and more, right? By the time you take 15 people, all of the estimates are between 2 and 3, right? Nobody's more than like half off. Okay, everybody's within about 0.5 of the truth. Whereas when we started, the range was like from 1 to 4. So we've reduced that range. It's getting less variable. It's kind of keeping that normal distribution, that bell shape. Okay. So the point I'm trying to make here is that when you sample a population, a couple things happen. First off, regardless of the fact that we started with some weird distribution in our sibling data, by the time we took a few samples and averaged them out, the shape became bell-shaped. And that'll actually always happen. So when you sample from a population and you average out a bunch of people, those averages are going to start to take on a bell shape. And they're going to be piled up around the true mean, like right around 2.4. And the more people you take, the closer you will be to the truth. It's going to be less variable. And the normal distribution part is just like a nice bonus because we know how to calculate, probabilities and stuff with normal distributions. If I were to calculate the mean of all of these, what do you think it would be?
2.5.
Yeah, notice. What's the actual number of siblings?
2.42.
2.4, right? Sorry, in each step, here we were a little bit off. Here we were a little bit closer. Here we were even closer. But on every single stage, they're all pretty much getting it right on average, right? So on average, you'll get it right. Sometimes you'll overestimate it. Sometimes you'll underestimate it. But the big thing you see with the higher sample sizes is that they have more of a normal distribution, and the variability is a lot lower. So that's the advantage of taking bigger sample sizes. Okay. All right. So the whole point of this, okay, is this is basically what we did. Essentially, what we were doing is we were looking at a sampling distribution. Okay. So, if you remember, right, what's a probability distribution?
At or below.
That'd be a percentile,
Oh, percentile.
right? But a while ago, I defined a probability distribution, right? It shows all possible outcomes and their likelihood. Right? So for discrete, when we had discrete random variables, they look like tables. Right? When we had continuous random variables, excuse me. Jeez. Random variables, they look like curves. Right? So then what happens is, okay, well, what we just looked at, though, is when we took the sample mean itself had its own shape, right? If you take a bunch of sample means, I let a bunch of people come in here and calculate their own sample mean, and then we compiled all those sample means together. They themselves had their own shape. They had a normal distribution, and so a sampling distribution, that's the probability distribution of a sample statistic. Okay, so it's like the sample statistic itself is a random variable. Every time someone new comes in here and takes a sample of students and calculates a mean, they're going to get a different answer than the person before them. So it's a random variable. Like, you can't predict it ahead of time. But some values are more likely than others, and we saw it in the graph. You're more likely to get a number closer to 2.4 than you are to get a number further away from 2.4. And a normal distribution is the shape of that sample mean. Most people are going to pile up right around 2.4. A few people might get a really high estimate. A few people might get a really low estimate. Okay. So then, what we were looking at, all those graphs, those would be the sampling distribution of the sample mean. Okay. And what we saw is that it's always centered around the true mean, right? Because we happen to have the advantage of knowing the true mean. We knew the truth was 2.4. But we also observed that even if you weren't allowed to pick all of the people in the population, on average, though all those distributions were still centered around 2.4. So it's always centered around the true mean. And as n got bigger, what happened? Two things happened. What's one of the things that we saw? Yeah, so the variability or the spread decreased, right? You're getting closer to the average, right? What else happened? Yep. Yeah. Yeah. So there's two things going on. Not only are you always getting it right on average, which is good, that's what you want, but we know that the more samples you take, you can decrease your variability, so those guesses are going to get closer and closer to truth, and the shape of the distribution is going to become bell-shaped and normal. So this is actually something called the central limit theorem, and you can actually you can define the factor by which that variability goes down. So here's what the central limit theorem says. Okay. It says that for large enough sample sizes, then if you want to look at the sampling distribution of the sample mean, which we call X bar, it'll be approximately normal. Approximately normal or normally distributed. But for a normal distribution, you have to know two things about it. In order to like use the z table or whatever, what do you need to know about a normal distribution? You need to know it's, what are the two?
True mean.
It's mean and it's
Deviation.
standard deviation. Okay. Okay. So to know, we need to know the mean and the standard deviation. I'm going to use subscripts of X bar. So this is saying the mean of the sample means, right? So like where are they centered around? They'll be centered around the true mean. And the standard deviation of those true means, it'll be equal to the population standard deviation, but it'll be scaled. It is scaled by a factor of the square root of the sample size. So this is like the center of all the X bars we saw on the graph. This is the standard deviation of all the X bars. Okay. This mu over here doesn't have a subscript. This is the true population mean. And then that sigma right there doesn't have a subscript because it's the true population standard deviation. And little n is always the same. It means sample size. So, yeah.
Or basically, the mean of the means is
The mean of the means is the mean. Yes. It's saying that the mean. It's saying that the mean of the sample means will be equal to the true mean. That was the last little box I showed you. It's on StatCrunch. Yes, it's confusing. I won't deny that. It's saying that if you average, so like here, right? This was the original population. This was like a bunch of sample means where they sampled 5 at a time. This was a bunch of sample means where they sampled 10 at a time. This is a bunch of sample means. But if I averaged out all of these, and I averaged out all of those, and I averaged out all of those, what happened? They all came out to 2.4. So it's saying that the average of the averages, so even though some of them are above average and some of them are below average, if you average them all out, they're going to come out to be the true population mean, the 2.4 in that case. If you calculated their standard deviation, though, what you'd see is you see that every time you sampled more people, the standard deviation would go down because we saw all those graphs narrowing. And you can actually show it, but they're going down by a factor of the square root of the sample size. So the population had some standard deviation. We did it, I think it was like 1.5. Each one of those that we took would have a smaller and smaller standard deviation. All right, so how we're actually going to use this stuff, I'm going to show you tomorrow. But I just wanted to show you the pictures and kind of give you an idea of what's going on. And then tomorrow we'll actually use these results to calculate some probabilities and stuff. So, okay. Sorry for my incessant coughing. Hopefully I'll be a little bit better tomorrow.